All right, so we're going to continue on with our power series. So the first two examples we did about finding the radius of convergence, right? In order to do that, we're going to perform the ratio test on each of these power series. And the first example we saw where the interval of convergence was all numbers. So it converged for every single value of x you plug in. The second example we did, we saw where the radius was only 1. So I want to look at another one. And once you get the steps down for finding this radii, it's not too bad. The biggest issue you guys are going to have when you're doing these problems is when we set up the limit. Remember, n is the variable in the limit. X just stands for any constant number we want to plug into the function. So you have to make sure when you're evaluating the limit, you're treating the x's like they're constants, and we're treating the n's like there are variables. So if we look at this series, and you'll always know you're dealing with a power series because there's an x in it. All right, so we're going to have -1 to the n times x to the 2n plus 1 over 2n plus 1. So we're actually going to learn in the next section how to generate these power series, but that is actually sine of x. All right, that's actually what sine of x looks like if you turn it into a polynomial. And the reason I know it's sine of x is it's alternating. All the powers of x are odd numbers, right? And so sine of x is an odd function. So when you generate its polynomial, you're only going to get the odd powers of x. Similarly, when we do cosine, cosine is an even function. So you're going to see all the odd powers of the polynomial disappear down to 0, and you're only left with the even. So you get 1, 2, or x squared, x to the 4th, x to the 6th. So we're going to actually see how to build these in the next section. But what we want to do if we want to find the radius of convergence is we need to perform the ratio test. So the ratio test tests for absolute convergence. So we want the absolute value, right, of the nth plus 1 term over the nth term. So when I do the nth plus 1 term, when you plug n plus 1 in here next to the 2, it's going to roll out to be 2n plus 2, and then when you add it to the 1, you're going to get x to the 2n plus 3. So then the same thing's going to happen in the denominator with the factorial. When we divide, or by a fraction, right, we're going to multiply times the reciprocal. So because this is actually jumping consecutive numbers on the number line, it's going to be a little tricky when we deal with these factorials. So you got to pay attention to their powers. So the first thing the absolute value is going to do is it's going to wipe out these -1 terms. So we can just trash those right away because those terms will only be 1 or -1, and their absolute value will always be 1. So you can dump those immediately. All right? Then we need to simplify these factorial terms. So 2 to the n plus 1 factorial, right, compared to 2 to the n plus 3. 2 to the n plus 3 factorial says multiply the first 2n plus 1 numbers, but then the next number on the number line is 2n plus 2 because they count up by 1. And remember, in factorials, you're not allowed to skip any digits. And then we get 2n plus 3. So what's going to happen is we can cancel the 2n plus 1, but we're going to be left with both of these terms in the denominator. So then what's going to happen is the x to the 2n plus 1 is really x to the 2n times x to the 1. And the 2n plus 3 is x to the 2n times x cubed. So the x to the 2n is going to cancel each other, and then this x in the denominator is going to cancel one of these in the numerator, so you're going to be left with x squared in the denominator. or in the numerator, sorry. All right, so when it's added, you can just split them apart like that. So now what's going to happen is we need to take the limit as this goes to infinity. So we have to look at what stays in absolute value and what does not. So the ends are just the counting numbers, 0 through infinity. So the denominator of this guy will always be positive. So the only thing we really need to keep in the in absolute value would technically be x, but x is squared. So no matter what value of x you plug into this equation, everything in this ratio is going to come out to be positive. So I can simply now take the limit as n goes to infinity of x squared over 2n plus 2 times 2n plus 3. So one other step you could do if you wanted, if you're worried about the x's, is you can pull them out front because they're constant. So this is really the limit of x squared times, or excuse me, x squared times the limit of 1 over this stuff. So the ends in the denominator are going to make this limit go to 0. When the limit goes to 0, right, which is less than 1, right, and the condition is we need to find out what values of x make this pass the ratio test. Well, this thing passes without ever knowing any value of x, right, because it's going to go to 0 no matter what. So what we can say here is that all values of x, this thing will converge. So the radius of convergence is infinity. So we can demonstrate that on a number line. This function was centered at 0. The center works, but so does every value of x from positive infinity to negative infinity. And remember, we measure the radius from the center out. So this is what an infinitely long radius would look like. This thing accepts all values of x. And if you know the domain of sine of x, because I cheated and told you that's what this was, sine of x accepts all values of x. So it shouldn't be crazy that its polynomial will as well. So finding the radius of convergence is great, but you want to think of the interval of convergence as sort of like domain and range. So when you found domain and range, you wanted to know for what values of x am I allowed to plug into this function. So knowing the radius is great, but we need to also figure out, well, what's going on at those endpoints? Because, right, if we have parentheses, we don't include the endpoints. If we have brackets, we're allowed to include the endpoints. So if we want to find the actual interval of convergence, right, which is sort of like finding the domain of the series that works, we have to not only find the radius, but then we have to actually test the endpoints. So I'm going to show you how to do that. And when you're plugging in the endpoints, what hopefully should happen is the series should turn into a recognizable series that you can look at right away and tell if it's convergent or divergent. So when we're testing endpoints, if you see the harmonic series come up, I don't need you to do a test to tell me the harmonic series diverges. You can just simply say harmonic series diverges, right? If we get an alternating harmonic series when we run the endpoint test, you can tell me, well, it converges because it's an alternating harmonic series, right? It's very rare that we get something a little weird and we have to actually run a test on it. But I don't want you guys thinking you got to run tests on everything. If you're not sure, you need to run a test, right? But it's okay if you recognize a p-series, a geometric, and as long as you tell me what about it tells you it's converging, I'm cool with that, okay? I just need to see some justification for your answer. So let's look at how to find our intervals of convergence. So the first thing we're going to do is find the radius, and then we're going to test the endpoints if necessary. So earlier I told you all of these power series will fit into one of three categories. Either they only converge at the center, and they all converge at their center. They have to, because that's what we built the series around. They either only converge at the center, which means the radius is 0, which means there are no endpoints. There's not even an interval. The interval is just a point, okay? Or you get an radius that's infinity, which means it's just the whole number line. So then there's no endpoints there. We don't have to test an infinity. But if we get a radius that's anything other than those two things, that's when we're going to have to test the endpoints. Now, keep in mind, both endpoints might work. Neither of the two endpoints might work, or it could be a combination of one or the other. Okay? So let's look at a series. Now I'm going to cheat again and tell you this is e to the x. So we're actually going to see how to build this the next section. But this is e to the x. All right, so if we look at this, the first thing we need to do is find the radius of convergence. So we're going to do that by conducting the ratio test. Oh, my bad, my bad. I wrote the series down wrong. This is an n factorial, so dump these factorial signs. I got a little ahead of myself. I got excited. Put that in automatically. So this is not e to the x anymore. E to the x is if it's n factorial, but this is just e to the x over n, okay? So what's going to happen now is, right, our x to the n down here is going to cancel the n, so we're still left with an x. So what we have now is n times x over n plus 1, because we couldn't cancel any of those n's. So now when we set up the limit, we know the n's are positive, so this is really the limit of n times the absolute value of x over n plus 1. So I need the absolute value bars around x, because x could be a negative number or a positive number, right? So what's the limit? Remember, I can take the x and pull it out front. So what's the limit of the n over n plus 1 stuff? 1. So this is just 1 times the absolute value of x. So in order for this ratio to pass the ratio test, we need this to be less than 1. So we set x to be less than 1. And there's two things you can do from here. The theorem says, well, if you get an inequality of the form x minus c is less than r, then you're allowed to say, well, there's our center and there's our radius, right? So I actually know this thing was centered around 0, because x minus 0 is just x, and r is 1, because that's the form of the theorem. If you have a trouble, like me, I used to really always have trouble with that. I just couldn't see it. I was more comfortable doing algebra. You can simply solve the inequality to find the interval endpoints that way. So if you wanted to solve this inequality, if the absolute value of x is less than 1, then you can drop the absolute value bars and say, well, then x is between -1 and 1. So that's actually, those are the endpoints of your interval. And if we map those on a number line, right, the center is always in the middle. So it was easy for me to find the middle number. So the center was 0, right? And we know everything between these values works. We just don't know what's happening at the endpoints themselves. So we do this by testing these values in the original series. So if we come back up, and we'll do -1 first. So I'm going to write the series from 1 to infinity, and it was -1 to the n. I'm just plugging it in for x over n. So is this going to converge or diverge? Why? It's going to converge because it is the alternating harmonic series. So this converges, right? It's the alternating harmonic series. So that means I can put a bracket at -1. We're going to include that endpoint. Now let's test it when x equals positive 1. So when x equals positive 1, you're going to get 1 to the n over n, which is just equal to 1 over n. This is the harmonic series, right? Not alternating. And so we know the harmonic series diverges. So that means I don't include that endpoint and I put parentheses around that. So your interval of convergence is -1 to 1. And we can see that the radius, is 1, right? And it's centered at 0. Right, any questions on that? Does it make sense how we did? All right, we're going to do another one because these take practice. You have to kind of practice them. But you'll see the process is the same every time. So you're going to perform the ratio test, find the interval, the radius of convergence, and then you're going to test the endpoints. Okay? So let's look at another one. And remember, the whole point of this is the functions that are creating these power series are usually pretty complicated to evaluate them on their own. But plugging it into a polynomial is pretty easy. So what we're finding are the values of x that the polynomial will accept. Right? We're just basically like finding the domain. All right? So if we look at this, we're going to perform the ratio test first. And does anyone know what the center of this power series is? You should always be able to see the center in the original series. It's -1 because the series, the center always takes the form x minus c. So if it were x minus 1, you know the center was at 1. If it's x plus 1, the center was at -1. So there's a reason you should always ask that question. When you find your interval, if -1 isn't right in the middle of your endpoints, you've done some algebra wrong. So there are sort of like checkpoints we can use along the way to make sure we haven't messed up or flubbed up the math, okay? So we know these absolute value signs are going to wipe out these -1s, so we can get rid of those right away. We know that 2 to the n is going to cancel the n in the bottom and leave us with 2. And we know that our x to the n, or x to the 1, x plus 1 to the n, excuse me, cancels the n out of the top. So all of this reduces to x plus 1 over 2. So all of our n's went away. But I still need to see the limit. And since this is just a constant, right, the limit of a constant is just itself. So you can't technically say, I know the radius yet, because the theorem says it needs to be of the form x minus the center is less than one number. But we know in order to pass the ratio test, this thing needs to be less than 1. So I can do one more line of algebra. And now I'm of this form. So if you're good at reading it here, what we're saying, right, is the center is -1 and the radius is 2. So you can draw the number line and count 2 spaces away from -1 on either side. I personally get comforted, like I said, by the algebra. So I would solve the inequality and I would say, well, that means x plus 1 is between 2 and -2. And I simply subtract 1 from both sides and get my interval as -3 to 1. So -1's in the middle of that, and it's 2 spaces away from each of those numbers. Okay, so now we need to test our endpoints. So we'll do -3 first. So if x is -3, I go back to the original series and I plug in -3 for x. Oops, -3. So let's leave the -1 alone. And -3 plus 1 is -2 to the n on top, and I have +2 to the n on the bottom. So when you have two numbers, right, this could potentially be an alternating geometric series because I have a fraction of n's, but look what happens if I combine the 2's. Well, I'm going to leave the -1 out front, just leave that alone for a second. -2 divided by 2 is -1 to the n. You cannot say that -1, just don't, okay, so you can't just assume because you see a -1 to stuff times another -1 to stuff that equals 1, right? Because if that were n plus 1 on the left side and that were 1 on the right side, that may or may not be true. So always use your powers of exponents. So since these are raised to the same exact power, I am allowed to say that this is -1 times -1 all raised to the n. So this does work out to be 1. Does that converge or diverge? It diverges because it's just 1, 1, 1, 1, 1, 1, 1. It's going to end up at infinity, right? So this diverges because constant functions diverge. So it's just counting to infinity by 1, very slowly. All right? Let's look at what happens at x equals 1. Well, I'm going to get -1 to the n times +2 to the n over +2 to the n. Those cancel. Oops. And I just end up with the series -1 to the n. So we've actually looked at this one before. This one also, yep. Mm-hmm. It would, no. I mean, it would, but the powers of exponents say this. X to the n times y to the n is xy to the n, right? If I had -1 to the n raised to the n, you would multiply and get n squared, right? But when you have the same base, like you can do, it just ends up being +1, no matter how you stretch it, right? And even if it's to the 2n, well, that's always a squared term, so you're always going to get -1 squared, or -1 to the 4th, or -1 to the 6th, and those will always be 1. Yeah. So here, we've looked at this before. This is just the alternating series, 1, -1, 1, -1, 1, -1. And we said this diverges because it doesn't have a limit. The sums will either be -1, 0, or 1, depending on where you start and stop counting from. So this is also essentially a series of a constant, right? And so this is going to diverge. So neither of these endpoints work. So if we go back up, we can accept the values in between, but not the endpoints. So our final interval is -3 to 1 with neither endpoint included. It seems cumbersome, but you don't have to run any tests on the endpoints because usually these power series turn into something you've seen before. And they're pretty simplistic things that you've seen before. All right, so let's look at another one. We are finally going to do E. It's fun in the tutoring center when I'm, oh, my bad, it's not E again, dang it. I get all excited. It's coming up later. It's x to the n over n squared. So let's look at the ratio test for this guy. So we're going to get x to the n plus 1 over n plus 1 squared, right, times n squared over x to the n. The x to the n cancels the n up top, and so what I'm going to be left with is n squared over n plus 1 squared times the absolute value of x. So what we can do, since these are both squared, it's probably easier to write it as a ratio of both things and then square it, because it's easier to do the limit of the stuff inside, right? Times the absolute value of x. So what's the limit of the stuff inside the parentheses? 1. So we get 1 squared times absolute value of x. So this limit just equals the absolute value of x. It converges if it's less than 1. So we can see that the center is 0 and the radius is 1. And if I set up the inequality, I'm just going to get x's between -1 and 1. So we can go straight to drawing our interval. And I always like to label the center just because I like to double check that I did that right. All right, so let's test -1. So we go back to our original series. We're just going to get -1 to the n over n squared. So what is that? What type of series is that? It's a p-series, right? And so if p is greater than 1, they converge absolutely, meaning p is 2, right? It's greater than 1. So it'll converge if it's positive, and it'll converge if you alternate it. So we can simply say that this converges, right? It's a p-series where p equals 2. So that's the beautiful part about a p-series. If p is greater than 1, it will converge in any form, okay? So we know we get to include -1. So let's test 1. Well, that's even easier because +1 raised to any power, right? So there it is again. So on one end, we got an alternating p-series. On the other end, we got the regular version of the p-series. So this converges as well. So you don't have to write it again. You can just say that works for both, right? That explanation satisfies both. So if we go back to our interval, we get to include both endpoints. So the interval is -1 to 1 included. All right. Any questions on these? So you've seen a lot of examples, one where the endpoints didn't count, one where the endpoints both counted, one where we had a mixed bag, and we saw some where the center is 0. We saw some, where the radius was 0, where the radius was infinity. So in the 0 and infinity cases, there are no endpoints to test, all right? All right, so the last thing I think we're going to go over, yep, the last thing in this section are the reason we like power series so much, okay? Well, what if I need to, these are usually taking the form of transcendental functions. And like I said, you'll see this in the next section when we actually build these from scratch. But what if it's like sine of x, e to the x, and I have to work with it, right? And I want to know something about the integral of those functions or the derivative of those functions. Well, polynomials are really easy to integrate and really easy to differentiate. So we can actually find the interval of convergence for the integral of a function, the function itself, or the derivative of a function. And to make this a little easier, we're going to look at a function that we just looked at. So x to the n over n. So we actually just did this function, and we saw when we set this guy up, right, we saw earlier that it converges at -1, right, and all values up to but not including 1. So for the integral, right, let's look at the integral first. So since this is a power series, right, we can integrate each term using a power. So we can actually integrate it in the form of the series itself. So x is the variable we're integrating with respect to. So if we want to integrate this series, how do you integrate x squared, right? You add 1 to the exponent, and then you divide by that exponent. So you can actually think of this as 1 over n times x to the n. So you add 1 to the exponent, and then you divide by that exponent. So you've just integrated an infinitely long series polynomial. We just did it with the nth term. It's just a power rule. So now, if we wanted to look at this series and see where it converges, right, we would simply perform the ratio test. So now I'm going to have n plus 2, right, over n plus 1 times n plus 2 times n plus 1 over x to the n plus 1. So my n plus 1 cancels. My x to the n plus 1 cancels and just leaves me with 1 here, because this was x to the n times x. Up top, it was x to the n times x squared. The x to the n's went away, and the extra x in the bottom only left me with 1 in the top, right? So the limit we're going to look at, I just have an x in the numerator, and then I have n over n plus 2 is all that I had left. So the limit of this is just the absolute value of x. This has to be less than 1. So notice we get the same interval that we saw before. But in the original series, we found that it worked at -1, but it did not work at +1. So we have to see if that's still the case with our new endpoints. So when we plug in, remember we're testing the new series we made. So when x is -1, we get -1 to the n plus 1 over n squared plus n. So the reason I distributed the n in the denominator is I wanted you to be able to see the highest power of n. Okay? So if you were going to compare this, doing limit comparison, what would you compare it to? Right, all the -1 in the numerator does is alternate it, but what's going on in the denominator? What's the highest power of n you see? P series, right? So whenever you got polynomials, all you care about, because remember we're going to look at the limit as n goes to infinity, the n is never going to catch up with the n squared. So we're just going to look at the n squared. So this is a form of a p-series, right? And that p-value is greater than 1. So if we wanted to show convergence, I could actually test for absolute convergence by taking the absolute value, comparing it to the p-series, and you would see that it converges. But I'm okay if you're testing endpoints, if you recognize that that's just a p-series of p2, I don't need to see the test, right? Unless I ask you to test for me, right? So at this point, after you've done a bunch of these p-series, you should be recognizing these. So we can actually see this converges. Furthermore, if we try x equals 1, we're simply going to get 1 over n squared plus n, and that's just the positive case of the same p-series. So since p is greater than 1, both of these converge. So this guy works at both endpoints. So if you go back and look when we actually did this test for the original function, we ended up with some version of the harmonic series at the end. When we did it for the integral, we ended up with n squared. And if you think about what integrating does, it raises your exponential power by 1. So that shouldn't be a big surprise that we ended up with a p-series one power higher when we did that. Make sense? Okay. So if we wanted to do the derivative of the series, so this is pretty wild. In the same way, we took the integral of the term itself, we can now differentiate the term. So the derivative of x to the n, right, is just n x to the n minus 1, right? And we still had that n in the denominator. Those n's cancel, and all you get is this. So there are no n's left except in that exponent. So if I did the ratio test, I would end up getting the limit is some form of the absolute value of x again, which means the radius is still just going to be negative 1 to 1. So I'm going to kind of leave this as an exercise. But if you actually complete the problem, the interval of convergence you get should be that. You should see that it doesn't work at either endpoint. So you can set up the ratio test, perform the limit. There aren't any n's to get in your way. And you should see that when you test the endpoints, they diverge at each endpoint. All right, so we'll stop here to do a quiz. This is the end of this section. So when we come back on, let's say Wednesday, when we come back on Friday, we'll actually see how to build a Taylor series off of any function that we want, that we need them for. Now there's one other series we didn't see when we tested here, and sometimes when you test the endpoints, it looks like it could be a geometric series. So if it looks like it's a geometric series, right, we know that that only converges when the thing that you're calling the R value is less than 1, right? And so then you can set that up and solve the inequality that way. All right, but let me pull up the quiz problems. And this will be on the ratio test, which will be great practice because you have to use it to do this stuff. All right, and then we'll have a quiz on this stuff on Friday. Fine, here we go. So this will be quiz 13 for you guys. I think it's, yep. This is a nice, short, sweet one. So all you're going to do on these problems is determine if they converge or diverge, and you have to show your work, which means you have to perform either the ratio or the root test, because this is the section these came out of. If you find another test that works, I might allow that too, but I want to know why. And remember, if your ratio or root test equals 1, it's inconclusive, and you have to find another test.